Hello and welcome to this special course named A Practical Guide to Railway Steel Girders.
So let's start with understanding the objectives of the course. For whom this course has been designed and how can you get benefited most out of this course. So if you are a designer or bridge engineer or a professional engaged in construction inspection or maintenance of railway steel bridges, I would just request you to take a step back and first try to understand the railway steel girders from their load transfer arrangement point of view. It will build a deep understanding within you about how these girders are currently being conceptualized and how you can improve them. Now, at present, what I am finding is that our most online courses are focusing on design aspects mainly. Design aspects of these railway bridges are mainly being taught in various online courses. In general, there is a lack of basic foundation course covering other than design aspects of different types of railway steel bridges, covering practical field aspects of these bridges. So the design courses, which are basically focusing on design aspects, are generally of very little use to other bridge domain professionals who are engaged into inspection, fabrication inspection, maintenance, or construction of these bridges. So this course has been designed to provide a practical understanding of railway bridges for such professionals. It will prepare the attendees for advanced bridge courses. So in this course, we have first covered most commonly used railway steel girders, that is open web girders, steel plate girders, and composite steel plate girders. These three types of girders are most commonly used railway steel girders. Then there are new developments in railway steel girders like road cum rail bridges and ballasted deck open web girders. So briefly, we have tried to cover these two kinds of new developments as well. Apart from this, track structure over bridges is quite untouched topic, but it's a very important topic for the bridge professionals. Why? Because with the introduction of LWRs, that is long welded rails, CWRs, continuously welded rails, and concepts like RSI, rail structure interaction, we have to have an understanding of how track interacts with our bridge superstructures. So we have tried to cover this track structure over bridges in detail in this course also. So how the course structure has been set up. So the course is mainly divided into three sessions. The number one is introduction. Number two is types of railway steel girders. And number three is track structure over bridges. In introduction, we have covered some basics about railway steel girders. Then, what are different types of steel girders? Brief introduction of these girders because in session 2 we are going to cover these in very much detail. Then we have tried to introduce the topic of design loads for which these girders are designed. Then in session 2, railway steel girders, we would be covering open web girders, plate girders, and composite steel plate girders in detail. In detail means we would be covering these four aspects for each use case: the general arrangement, detailing of components, Understanding the load transfer from rail wheels to girders, then substructure, and then foundations. And what are the bearing options for each and every type of these girders? Then we have tried to cover briefly rail cum road bridges. I have covered rail cum road bridges through two examples. Then I have touched upon ballasted deck open girders also. Then there is a topic called selection of a suitable girder. So, what are those parameters which define the use of a particular type of railway girder? So, we have tried to discuss around this topic also. Then, in session 3, that is the last part of the course, we would be dealing with track structure over bridges. I have tried to cover this particular topic with as much detail as possible and will try to convey as much knowledge around this topic as possible. So, with all this introductory part, let's start. Hello. So, let's start with the basics about railway steel girders. So, let's start with defining a railway bridge. So, a railway bridge is a structure designed to carry freight and passenger trains across an obstacle in the landscape. A railway bridge is a structure designed to carry freight or goods and passenger trains across an obstacle in the landscape. So, normally, the loading for which a railway bridge is designed is defined by freight train or goods train because the axle load of a freight or goods train is much more than the passenger train. However, the speed potential for which a railway girder is designed is defined by passenger train. Why? Because the speed of a passenger train is much more than the freight or goods train. Then come to the latter part of the definition. Across an obstacle in the landscape. This obstacle in the landscape can be a water body or the land itself. So when a railway structure or is built across a water body, it is called technically a bridge. And if it is built on land, it is called a viaduct. So metro railway structures are basically nothing but the viaducts. So if there is a river and then there is a land and we build a bridge over here like this, and then what happens that normally this bridge approach, or you can say the river approach, is normally on gradient. It is increasing from normal ground level from here to here, from here to here. So what we will have to do to match the levels of normal bridges, we have to ramp it down in the approaches. So the viaduct can be this can be named as viaduct. This portion can be named as viaduct because it is built upon the land. Now let's understand minor, major, and important bridges. So basically, this classification is done based upon the length of waterway the bridge crosses. If it is crossing a minor length, a small length, we can call it a minor bridge. If it is crossing an intermediate kind of length, it is it can be defined as major bridge, and if it is crossing a large river, large water body, large waterway length, it can be called as important bridge. So normally the bridge owning organizations, they define the limits in meters for these waterways so that their bridges can be classified. Why this classification is necessary for these organizations? Because this categorization helps these organizations in standardizing the superstructure types and in defining maintenance schedule and practices. So organizations have one sets of maintenance practice and inspection schedules for one type of railway bridges, minor, major, and important. Now let's talk something about the steel used in girder fabrication as per IS 2062. So normally E250 grade steel is used in the design of railway bridges. This E250 is defined in IS 2062. When sectional requirements increase to large extent, our section becomes heavier and heavier. Then to reduce the section, we need higher grade steel. Now higher grade steels can also be used in railway steel girders like E350 and above. Now let's come to the quality of steel. Preferred quality of steel is B0 grade. However, in exceptional cases, grade BR can also be allowed. Now let's come to the grade C steel. So grade C steel is to be adopted in the areas where sub-zero temperatures are expected. And grade A steel is not permitted, not to be used in railway bridges. Now let's discuss something about the fabrication and erection of these steel girders. Generally, the components, generally the components of the steel girders are welded in the workshop. So components are welded in the form of built-up sections in fabrication workshops, and then components are assembled at site with the help of bolts. So components are welded first and then they are joined together or assembled together with the help of bolts. However, there can be other arrangements also. We can have fully welded structures as well. So where components are welded in fabrication workshops and at site also they are assembled with the help of welding only. So here field welding is involved. So here one thing is to be taken care of that in workshops we have stricter quality control. So if we are doing welding at site, more strict quality controls are necessary in the field. So this was to cover basics about the steel girders. Now let's move on to the types of steel girders. We will try to discuss the various types of steel girders in brief because in any way we are going to cover it in the session 2. Just for introduction's sake, I am trying to cover types of steel girders in very brief here. Thank you. Yeah, so now we are here. Now we will discuss types of steel girders in brief. So let's start. This is the first type of railway steel girder. This is the through type open web girder. So why through type? Through type means the train passes through the girder, not above it. So the train passes through the girder. That's why they are called through type girder. then passes through the girder. Then open web. Open web means just the opposite of solid web. As we have solid web plate girders, in contrast to that, we have open web truss girders like this. So as you can see, the web of this truss girder is open. So that's why open web. So probably these kind of through type open web girders are the most commonly adopted railway steel girders. So railway transportation system adopts these kinds of open web through type girders uh, very often. So apart from through type open web girder, there is another kind of open web girder also, which is called underslung type, underslung type open web girder. Underslung type open web girder is just reverse in orientation when compared to through type open web girders. Nowadays, these underslung type open web girders are not much in use. There are two, three reasons behind this. The number one thing is their design and sections are quite complicated and they are difficult to fabricate also. And they are difficult in fabric, not only in fabrication, but erection and launching also is quite tough when it comes to underslung type open web girders. And number three is whenever we cross a river body like this, there are always certain navigational requirements which we have to mandatorily follow, like freeboard. Freeboard is the clear height available above the highest water level up to the bottom of the girder. So this is for navigational purpose, and this freeboard requirement we have to have in our planning. We cannot avoid it. So what happens here, this freeboard requirement gets added to the with the height of this girder because the freeboard requirement is eaten away by the depth of the girder. So naturally we have to make longer piers when it comes to planning with underslung type girders. So this makes our bridges a bit uneconomical in the sense that we have to provide longer piers, piers having more height just to accommodate this depth of girder because from bottom of the girder we have to provide the mandatory requirement of freeboard. So because of all these reasons, the underslung type girders are no more in practice, only where they have already been provided from replacement point of view or maintenance point of view. Railway systems are keeping them. Let's move on to the next type of girder. This is very common type of plate girder. This is called plate girder. So this is nothing but basically two eye sections joined together with the help of bracings and over which sleeper, channel sleeper or H-beam sleeper, whatever they are, basically steel bridge sleepers are provided and over which rails are provided. So here this is plate girder. This is our plate girder. over which bridge sleepers have been provided. These are the bridge sleepers, and over which this track has been provided. Now you can see that here there are two spans. This is one span peer to peer, and this is another smaller span. So if we call this L1 and we call this L2, so L1 is greater than L2, so span L1 is more in length in comparison to L2. So as the length increases, depth of girder also increases. When the span length is less, girder depth is also lesser because we have the requirement of greater sectional area for longer spans. So what happens as the spans keep on increasing, the depth requirement of plate girder keeps on increasing. So again, this is okay for certain length of span, but after a certain limit, this depth becomes so much that if we provide those kind of plate girders, our rail levels will keep shifting higher and higher because again we have a certain minimum requirement of freeboard where again we cannot go below this level, for example, as far as our bottom flange is concerned. Now, if we have larger depth of plate girders, so like this we have to provide, then for more length like this we have to provide. So the track level will keep on increasing, and again for increasing track levels I have to ramp them down in the approaches. So again overall system becomes uneconomical. Not only uneconomical, higher depth of plate girders is otherwise also not desirable from stability, web stiffening, and torsion point of view. So normally up to 30-meter or so, these plate girders are quite suitable and they are very much used. And beyond 30-meter, we adopt through type open web girders. Now there is another kind of steel girders which are called composite plate girders. Composite means we are combining the effect of RCC and steel to mitigate our loads and forces. So what we are doing here, we are providing two plate girders in pair, and above them we are providing a deck slab of RCC. So the advantage of providing RCC deck slab over the plate girders is that we can continue with the same system of track which our ordinary track has. So normally concrete deck is provided over steel girders and track is provided over stone ballast with ordinary PSC sleepers. You will get more clarity on this when you look at this picture. On the left hand side, this is basically our steel plate girder, and above this we have this deck slab. Now, if we look at the picture on the right hand side, from here up to here, we have normal track laid over earthen embankment. And after this, you can see this parapet wall, which means we have composite steel plate girders over here. So you can see that I am able to continue the same track structure over my bridge also. So this not only this is not only desirable from continuing our already existing track structure over the bridges also. Overall, also these composite steel plate girders are much more stable and quite suitable for higher speeds also. So this was a little bit brief about composite steel plate girders. Now let's see some more types of steel girders. This is a rail cum road bridge. Rail cum road bridge means the bridge is catering to the rail transportation as well as road transportation. So as you can see on the top, here some street lights are there, here some vehicle is there, here people are here. So road system has been provided on top and railway system has been provided at the bottom tier. This is clear from this section where a road system is provided at the top and train system is provided at the bottom. This is quite obvious so that um, the heavier traffic loads have been kept at a lower level to keep our lever arms and forces within reasonable limit. And this arrangement makes overall girder economical. So, and this you can see that all this is a fully welded structure. Nowhere you will see there is a gusset plate or some bolts or something like that. This is a fully welded structure and train is passing at lower tier and road is passing at the upper tier. So this is one example of a rail cum road bridge. Let's see another example of rail cum road bridge. This is basically a bolted structure, as you can see. Again, the road system has been provided at the top, as you can see, and some construction equipment. Since this photo is at the time of construction, and the train system is at the lower level. So this is another example of rail cum road system. Here components have been welded at workshop and they have been assembled with the help of bolts at site. So this was the second example of rail cum road bridges. So with this brief introduction of some types of steel girders, this lecture is finished and now we will move on to introduce you to the design loads taken for the design of railway steel girders. Bye bye. Hi. So in this lecture, we will deal with the topic of introduction of design loads. So there are 13 types of design loads which needs to be taken care of while designing a railway steel girder. These are dead loads, live loads, impact effect, forces due to curvature and eccentricity of track, temperature effect, resistance of expansion bearing to movements, longitudinal force, racking force, force on parapets, wind pressure effect, forces and effects due to earthquake, erection forces and effects, and derailment loads. So let's start and deal with these one by one. Let's see what are they. So dead load. Dead load is the weight of the superstructure itself together with the permanent loads carried thereon. Live loads. Live loads of trains and road vehicles combined or individual as applicable. So if it is a rail cum road bridge, then we have to take care of both the live loads that is train loads as well as road vehicles loads. And if it is only a railway bridge, then we have to take care of only the train loads. Then we have impact effects. The augmentation in load due to dynamic effects should be considered by adding a load equivalent to a coefficient of dynamic augment, that is CDA, multiplied by the live load, giving the maximum stress in the member under consideration. The fourth one is forces due to curvature and eccentricity of track. So for ballasted deck bridges, even on straight alignment, an eccentricity of center line of track from designed alignment up to 100 mm shall be considered for the purpose of designs. Where a track or tracks on a bridge is curved, allowances for centrifugal action of the moving load shall be made in designing the member, all tracks on the superstructure being considered as occupied. Then we have temperature effects, where any portion of the structure is not free to expand or contract under variation of temperature. Allowance shall be made for the stresses resulting from this condition. The temperature limit shall be decided by the designer. Resistance of expansion bearings to movements, where the frictional resistance of the expansion bearings has to be taken into account. The coefficients are considered in calculating the amount of friction in bearings. Seventh, longitudinal force. Where a structure carries railway track, provisions as under shall be made for the longitudinal loads arising from any one or more of the following cases. A. The tractive effort of the driving wheels of the locomotives. B. The braking force resulting from the application of the brakes to all the braked wheels. C. Resistance to the movement of the bearings due to change of temperature and deformation of the bridge girder, roller, PTFE, or elastomeric bearings may preferably be provided to minimize the longitudinal force arising on this account. And D. Forces due to continuation of LWR, long welded rails, or CWR, continuous welded rails, over the bridges. Eighth, racking forces. Lateral bracing of the loaded deck of railway spans shall be designed to resist, in addition to wind and centrifugal loads specified, a lateral load due to racking forces as a fixed value and treated as moving load. So racking force is basically the force exerted by this rail flange when it strikes the rail heads. Okay. So during normal movement of the trains, these flanges keep on striking the rail heads and put pressure on them, and subsequently this pressure gets transferred to the bridge. So this lateral load need not to be taken into account when calculating stresses in chords, top chord and bottom chord, or flanges of the main girders. Forces on parapets. Railings or parapets shall have a minimum height above the adjacent roadway or footway surface. They shall be designed to resist a lateral horizontal force and a vertical force of 1.47 kN per meter or 150 kg per meter applied simultaneously at the top of the railing or parapet. These values have been taken from Indian Railway bridge rules. Now, wind pressure effect. Wind pressures are expressed in terms of basic wind pressure, which is an equivalent static pressure in the windward direction. In choosing the appropriate wind velocity for the purpose of determining the basic wind pressure, due consideration shall be given to the degree of exposure appropriate to the locality and also to the local meteorological data. So normally, the country is divided into various wind zones, wind zone 1, wind zone 2, wind zone 3, and accordingly, basic wind pressures in these wind zones are predefined by meteorological department. Then forces and effects due to earthquake. Seismic forces are evaluated and design provisions are kept as per relevant seismic code. These depend upon the earthquake zone in which the proposed bridge is situated. Erection forces and effects. The weight of all permanent and temporary material, together with all other forces and effects, which can operate on any part of the structure during erection, shall be taken into account. Allowances shall be made in the design for stresses set up in any member during erection. Such stresses may be different from those which the member will be subjected to during actual working. This is very important. Derailment loads, etc. So, forces due to accidental impact from any vehicles, such as a road vehicle, ships, or derailed train vehicles using the bridge. So overall, the design stresses are basically a combination of these three stresses arising out of combination of these loads and forces, secondary stresses and fatigue stresses. So this is a brief about what are the design loads and what are the design stresses that are considered in the design of railway steel girders. Thank you. Yeah, so welcome again. So far we have finished the introductory part and now we will start this railway steel girders. To start with, we will first cover open web girders through type, and to cover this, we will cover all these four aspects of general arrangement, detailing of components, understanding load transfer, and bearings of girders. So let's start with the general arrangement. So this is what open web girder through type looks like. So these are the most commonly adopted railway steel girders on a railway transport system. So let's understand it very carefully because this is going to be used quite often in the railway transportation system. So to understand this open web girder, we can think of this open web girder as a combination of two trusses. One is this truss and another is this one, which is hiding behind this. Another is this one. So these two trusses are connected at top, wide various members, and they are also connected at the bottom with flooring system. So this is what constitutes a typical open web girder through type. So what are the main components of an open web girder? So the bottommost member of the truss, this one, this is called bottom chord. The topmost member of the truss, this is called top chord. So for just for your information, this bottom chord as well as top chord, these are fabricated in parts. One part, one part, one part, like top chord also, one part, another part, and they are connected at joint with the help of bolts. With the help of bolts. So it's not like entire top chord or entire bottom chord is getting fabricated in one piece. So basically the section of the bottom chord and the section of the top chord are fabricated in parts and then they are assembled with the help of bolts at site. Now, with the help of this knowledge, you may also understand that if we want, we can do some economization or we can achieve some economy in designing the bottom chord or top chord, keeping the sections heavier for the middle portion, then lighter for next two portals and lightermost at the end. So like this, we can economize also. So this was about top chord and bottom chord. Then the last member which connects the top chord and bottom chord is this is called end raker. These are end rakers. Okay. And the vertical members which connect top chord and bottom chord like this. These are all called verticals. These are all verticals. Then we have diagonal members also. So again, I can show you. These are our diagonal members. These are our diagonal members. Yeah. So basically, the main members of truss are top chord, bottom chord, end raker, verticals, and diagonals. This makes my one truss, and similar kind of truss. Another truss is joined by various members at top and at bottom to make an open web girder. So let's see some more components. This is the flooring system of an open web girder. So this is the flooring system of an open web girder. So these are the bottom chords, right? These are the bottom chords. These two are the bottom chords running. These two are joined at various places at all the nodal points. They are joined by a cross girder. Which one is the cross girder? This is the cross girder. This is the cross girder. Where is the next cross girder? This is the next cross girder at the next panel point. This is the next cross girder. So these cross girders are being provided at all the panel points. So this is how at floor level, at bottom level, the both trusses are connected with each other. Then what are the stringers? Stringers are the members connecting two cross girders. So between two cross girders, as you can see, between two cross girders, we are providing a pair of stringers. This is a pair of, this is one stringer and this is another stringer. Stringer are nothing but the rail bearers. So basically, just above them, rails come. So this is one pair of stringers. This is another pair of stringers. This is another pair of stringers. So this is a system of cross girder stringers, cross girder stringers, cross girder stringers. Apart from this, bottom chords are also connected with each other with the help of bracings. So the bracings, these are the bracings. Okay, these are the bracings. So the bracings which connect bottom chord with each other are called bottom lateral bracings. Similarly, bracings which connect top chords with each other, those are called top lateral bracings, TLB. Okay, now let's see the floor system of an open web girder in detail. So this is the floor system. So as we have discussed that we have many cross girders. These are the cross girders. Okay, these are the cross girders. So cross girders are then connected with each other with the help of stringers. Here there are stringers. Then again a cross girder is here. So over the stringers, these steel sleepers are kept. These are the steel sleepers from here to here, or this one from here to here. This is one steel sleeper. So sleepers are something over which all the accessories are fixed. So these accessories are fixed on the top of steel sleepers which are resting on stringers. Okay, so stringers are basically like this, and over them these steel sleepers are resting, and over them we have rails like this. Now, you can see there are two pairs of rails. So one is guard rail and another is running rail. So this one is running rail. These are the outer ones. These are running rails, and the inner ones are guard rails. So running rails are something over which actually wheel of the train runs. And what are guard rails then? Why they are provided? They are provided over bridges. As you can see that they have got terminated over here, and after this there is no guardrail. So why they are provided on the bridge? So in case of derailment of wheel, either left hand side or right hand side, the wheel gets caught between the running rail and guardrail so that it cannot topple, and since it cannot topple, so it cannot damage much of the other bridge members like verticals and diagonals. So it protects the bridge in case of derailment. This is the main function of the guardrail. So guardrails attempt to contain the damage due to derailment by virtue of holding the dropped wheel in between running rail and guardrail. It arrests the toppling of vehicles. Then there is one more thing which is called inspection pathway. Inspection pathway is bolted on steel sleepers at many places like this, and it is meant for walking of inspection workers, or or some fabrication workers over the bridge. So the inspection people, the professionals engaged into inspection of bridges, can walk easily over this, and they can keep on inspecting various bridge members, their connections, the actual bridge health, track health, and all these accessories, how they are functioning, and what is their structural health as such. Now, if we remove all the steel sleepers from the bridge, then we can now see the stringers and cross girders. So this is cross girder, this is cross girder here, this is a cross girder, and these are the stringers, these are the stringers, these are the stringers. Again, this is the stringer. So this is a stringer cross girder arrangement. And as we are seeing this girder from the very end, so we can say that this is end cross girder. This is end cross girder. So now you can easily see what is the arrangement among cross girders and stringers, and you see it carefully. These stringers are also connected with each other with the help of various elements. We can call it a stringer bracing system. Stringer bracing system. And don't bother much about these members. Don't bother much about these members because these members are for connecting this inspection platform with the open web girder. So they are optional. somewhere they can be provided if required, and if they are not required, they are not integral structural part of the this open web girder structural arrangement. So you can simply avoid them. Do not think about them as some structural element related technically with open web girder structural arrangement. So we have seen the basic flooring system, track arrangement. Now let's see at the top. So at all panel points, the top chord is connected. At all panel points, top chord is connected with each other with the help of these sections. So these are called sway girders. These are called sway girders. Then below these sway girders, we have sway bracings. We have sway bracings also. So if I can mark it, sway bracing is something like this, this, and this. This is sway bracing. These are sway bracings. And at the end, we have these end rakers, right? These end rakers. So the top girder which connects these two end rakers is called portal girder. Is called portal girder. This was sway girder and this is called portal girder. And the bracing associated with portal girder is called portal bracing. Portal bracing. This is portal bracing. So we can easily remember this. Like we have portal girder and associated bracing is called portal bracing. We have sway girders, associated bracing connection is called sway bracings. Then in between two portal girders, in between two sway girders, we have this cross arrangement of top lateral bracing. So these are called top lateral bracings. Somewhat visible, somewhat not visible. So these are top lateral bracings. Okay. So just to repeat these things, we can say that this is end raker, this is end raker, these are verticals, these are verticals, these are diagonals, these are diagonals, this is bottom chord, this is bottom chord, this is top chord, this is top chord, and this is portal girder. These are portal bracings. Then we have sway girders. Sway girders are here. These are sway girders and associated bracings are called sway bracings. So let's move ahead. Now we can, with the help of this knowledge which we just acquired, we can start looking at the drawings of a typical open web girder. So this is elevation, half elevation of a typical open web girder. So here there is support at L0. We can say we are typically marking this start point at L0. Then we have L1, then we have L2, L3, L4. These are all lower joints. That's why there is a prefix L. And these are all upper points. That is why prefix U1, U2, U3, U4, U5. So we can easily understand that this bottom chord is fabricated and designed in parts. So bottom chord fabrication members would be like L0, L1, L1, L2, L2, L3, like this, and top chord members would be like U1, U2, U2, U3, U3, U4, etc. Then to connect top chord and bottom chord, we have end rakers. This is end raker. We have verticals. These are verticals. Then we have diagonals. These are diagonals. These are diagonals. And as you can see, uh, at these joints, two diagonals, one vertical, and two bottom chord members are getting connected with the help of a gusset plate. So this is the basic arrangement of a truss of a typical open web girder. Then let's see the bottom plan and top plan of a typical open web girder. The lower half, this lower half portion represents bottom of open web girder, and this upper half represents top plan of an open web girder. So let's first see the bottom plan. So at the bottom we can see this bottom chord member. These are the bottom chord members. Then we can see bottom lateral bracing. This is this one is bottom lateral bracing. They are connected with each other with the help of suitable gusset connections. We can also see in the bottom plan stringers. These are the stringers, right? These are the stringers. Okay. Since it is the half bottom view, so we are able to see only one stringer. Then we can also find half length of the cross girders. These are the cross girders. Yeah. So this is how our bottom floor plan looks like in open web girder. Now let's talk about the upper half, that is top plan of an open web girder. So in the top we can find this top chord member. This is another top chord member, another top chord member, another top chord member, like this. Then we are also able to see top lateral bracings. So this is a top lateral bracing. This is top lateral bracing portion. Okay. This is half. Then we can also find this, if we see carefully, this would be end raker if we are seeing from the top. This would be end raker, and the girder associated with the end raker joining two end raker points here and here, it is portal girder. This one is portal girder, and the bracings associated with portal girder, these are called portal bracings. Okay, this is a set of portal bracings. So this is how we are able to read the drawings of open web girder. Now we can also see the cross section of an open web girder. So on the left hand side we have half end view, and on the right hand side we have half sectional view. So let's talk first about half end view. This is half end view. Okay, so this is the So if we see at the half end view, what we will find is this is basically end raker. Then this box kind of section, this is top chord. Then we have this portal girder, and then we have portal bracings. Okay, we can also see on the right hand side, this is sectional view in the middle or somewhere in between. So here we can see that this is sway girder, this is sway girder, this one is sway girder. Then we can see that this is the top chord. Then we can see this may be a vertical, and here at both sides we can say that these are bottom chord members. Okay. Now, what is this shape? So, this shape represents maximum moving dimensions of the biggest vehicle which is supposed to pass through my open web girder. So, the dimensions of this body will decide what should be the minimum dimensions of my open web girder internally, because there are a certain set of dimensions of this vehicle, plus we have to provide certain clearances here and here and top. So with the help of these dimensions and clearances, we decide the minimum dimensions which will govern our open web girder dimensions. Now, in the last, we can see that here, this is basically a cross girder, okay, and these are the two stringers. These are the two stringers, okay. These are the two stringers. Over these, this sleeper is kept, right? And over which you can see there are rails. Yeah. So, this was about cross-sectional view of our open web girder through type. Let's move ahead. Yeah, this is an important concept in open web girders. When open web girders deflect, the shape of truss changes and the angle of intersection of forces also change. Therefore, stresses of the members also change. This introduces extra stresses in members, which we have not taken care of or which we have not conceptualized so far. To avoid this, the girders are fabricated with upward deflection, that is camber, such that the girder assumes the nominal shape under load. The girder assumes the nominal shape under load. In loaded condition, stresses in the girder are as computed for nominal shape. So overall, the idea is to construct or to fabricate an open web girder such that its shape is something like this. Okay, something like this. And when the load comes, when the train arrives and the load comes, it assumes the normal shape under load, right? Like this. Yes. So the upward deflection, this one, the upward deflection which we have given at various nodal point while at the stage of fabrication. This camber is given at the stage of fabrication. So this upward deflection which we have given, this is called camber. So this is calculated through various formulae and calculations, and designer who is responsible for designing of some open web girder, he provides the values of this camber under various loading conditions so that while at this stage of fabrication and assembly of the girders, you can make your girder according to the camber length given. So what happens? The fabrication of an open web girder is done according to camber lengths. Okay, according to camber length. So as you can see, for each member, there are two dimensions given. One is nominal and one is camber. One is nominal, one is camber. So if we talk about member L0 U1, so member L0 U1, this one, the nominal length is 13128 and cambered length is 13137.5. So actual member will be fabricated as per this length. Okay. The steel plate will have to be cut according to this shape. Okay. And when these are fitted with each other, the girder assumes this shape with as we wanted, right, like this, so that it achieves an upward deflection. How to check that we have done everything correctly, we have correctly put the cambered length. So there is a camber diagram given like this where you can find that yes, our camber which is being given is correct. So these are those values which are given. These are values given at each and every nodal point, that is L0, L1, L2, L3, L4, L5. So these values are given, and under different loading condition, dead load plus live load plus imposed load, live load plus imposed load, we have these values. One thing is to be seen that we do not want our flooring system to get disturbed because it has to, you know, it has to have a fixed dimension which is not getting disturbed under traffic. So what we are doing is we are keeping nominal length equal to camber length for all the floor members. As you can see, 7880, 7880. So this is same. The nominal length and camber length is same for all the floor members, right? So in general, this was about the general arrangement of open web girders. So we have finished up to here. This general arrangement part we have finished. Now we can start with detailing of components. So let's go ahead and start the lecture about detailing of components. Thank you. Hi. So far we have understood the general arrangement of open web girders, now let's begin the detailing of components. Now we will see the major components of open web girders in detail. So to begin with, let's start with bottom chord. So this is a bottom chord segment. This is also bottom chord. So a typical bottom chord of a open web girder is made up of two C sections, built up C sections, as you can see, built up C sections, and they are connected with the help of battens. These are the battens. Yeah. So this is the typical section of bottom chord of through type open web girder, and the design of these bottom chord members is primarily governed by tension because it is a tension member. Next in the list is top chord. So as you can see, this is the top chord of open web girder. A typical section of a top chord is something like this, inverted top plate and inverted L kind of thing, which are connected by some lattice and batten. This is primarily designed for compression loads. Then we have cross girders. So these bullets or these blue dots you can see, these are all cross girders. So this is one cross girder. This is basically another cross girder. This is another cross girder here. So these cross girders are designed for bending, and a typical cross section of uh, cross girder is given here. So it is basically an built up I section provided with the stiffeners in between. So stiffeners you can see on the cross girder. Yeah, here. Mm, yeah, this is a stiffener of a cross girder. Here also, it's so let's move on to stringers. So stringers are basically rail bearers because above them only channel sleepers, oh sorry, steel sleepers come over which rails are rested. So these are primarily rail bearers, and these are mainly designed in bending. So where are these stringers? So this is one is stringer. This is second stringer of this pair. Similarly, we have this one and this one. They are always in pairs. Typical section, if we talk about, then typical section of stringer is also a built-up I section with stiffeners in between. So stiffeners we are able to see here, here. So these are stiffeners. Okay. Then what is next? Next is verticals and end rakers. So end rakers are basically these members. These are mainly designed in compression and bending, and verticals. Verticals are these members, these blue dots. So these are vertical members. These are mainly designed for tension and as redundant members. So typical cross section of vertical is a built up I section, built up I section like this.
let's move ahead and let's see the first diagonals. The first diagonal is this one, right? And this one, okay. Blue dots are representing them. Then a typical cross section of this first diagonal is basically two C sections connected with the help of battens. These battens are provided one in front of the other. So two C sections connected with the help of battens. So you can see in the drawing also, this is a typical longitudinal section of a diagonal. So these are the holes to connect at L2 and these are the battens. And this is the top view of the uh, diagonal. So here also you can see there are two C sections connected with the help of battens. Yeah. So this was about first diagonals. Then we have intermediate diagonals. Intermediate diagonals have reversible stresses. So their design is guided by reversible stresses. They are basically the blue dots, as you can see from here also I can mark them. They are these members. So these are intermediate diagonals. This is also, this is also, this is also, this is also, this is also. And these are intermediate diagonals. So they are also basically inverted, oh, sorry. They are also a set of two C sections connected with the help of lattice. So, sorry, lacings. So lacings are used to connect these two members to form intermediate diagonals, and at the end they are connected with this batten plate, which is called end batten. So this is how our intermediate diagonal is formed. Then let's see stringer connections. So as we have seen earlier, stringers are always in pair, and these two stringers are well connected with each other. So typically in the middle they are connected with the help of this channel section ISMC. So this is ISMC here. It is. This is diaphragm, you can say. So this one see carefully. There is a ISMC here. Then there are other bracing members kind of arrangement also. So this is diaphragm ISMC, and these are angle sections. So this is how two stringers are connected with each other. These stringer connections are mainly designed for axial forces. Then we have sway girders. Sway girders are marked with these blue dots, as you can see. So these sway girders are designed for axial forces and bending, and their typical section is a built-up I section. A built-up I section, and stiffeners are provided if required. Here you can see. So this is a typical sway girder. Then we have portal girder, as we have discussed earlier also. Red dot is representing the portal girder, and this is designed for axial forces and bending. This is the typical I section, built up I section, which is used typically for portal girders. Then we have bottom lateral bracing. This is also interesting. This is bottom lateral bracings. These are designed for axial forces. So this is basically bottom lateral bracing. So as you can see, this is The section is made up of two angles. This is one angle and this is other angle. So these two are provided something like this. One angle, okay. This is one angle and this is another angle, okay. So we typically call it star section, okay. So this is a star section. So this is how bottom lateral bracing members are designed and connected. Then we have top lateral bracings. So depending upon the span and loading, this can be anything. The red dot is representing this cross bracing, top lateral bracing. So this is, in this particular case, we have angles to form top lateral bracing. Then, yeah, these are mainly designed for axial forces. Then let's move to the sway bracings. So sway bracings are, these are represented by this dot here, red dot. So basically this, and this, and this. So this is typically our sorry, sway bracing, and we have to design it for axial forces and bending. And depending upon the magnitude of axial forces and bending moments, the sections are decided. So this can be anything. So typically here sections are angles, and this is how their arrangement is made and drawn. So let's move on to girders in series. So after seeing the detailing of various components, let's come to the fact that typically open web girders need to be provided in series. So what happens that when one girder ends and another starts, maybe over a pair here, this is pair, like this. So there is a gap left. So if we do not provide any arrangement on this gap, okay, on this gap, then what happens that the unsupported length of the rail, suppose one girder ends, the sleeper of one girder is here and the next is here, and this unsupported length is too much. So generally the limit is 600 to 650 millimeter. So if it is beyond that, there are chances that the rail will get broken under the train loads. So how to solve this problem? So to solve this problem, we provide brackets. So brackets are not only necessary for girders where they are provided in series, but also even when there is a girder to be provided, there is a single girder to be provided. So what happens that at the end, this is my abutment wall. This is my abutment wall. This is abutment 1. This is abutment 2. This is my abutment wall. And where this ends, and here over the pedestal, we have bearing and we have this open web girder. So there is a gap because after this abutment wall, there is plain track over earthen embankment, and the next sleeper which it will get, it is far away. So what will happen? That rail will be unsupported from the end of open web girder up to the next sleeper, which is available on the existing track away from bridge only. So how to cater to this problem? So for this, brackets have been designed which are provided at the end of every girder so that the unsupported length of the rail at the end, basically between girder and abutment or pier to pier, if two girders are there on the pier, then girder to girder, it does not remain too much. So this unsupported length of the rail needs to be, controlled. So first case is for when a single girder is being provided between two abutments. The second case is for abutment, pier, and then abutment, two spans. The third arrangement is for abutment 1, P1, P2. Like this, there can be many, and at the end, we have abutment 2. So this is how bracket arrangement is provided. So how does a bracket look like? So let's see this. So this is the end cross girder and this is the abutment wall. So as you can see, there is this gap. Then we have abutment wall, and then after certain spacing, we will get first sleeper over here. So overall gap between the last sleeper and the first sleeper over here, this unsupported length of rail becomes too much. So as you can see, to solve this problem, uh, two brackets have been provided at the end, and these brackets are long enough to accommodate at least one sleeper. So this gives support to the running rail so that when it gets the next sleeper, this unsupported length is not too much and is within the limit of 600 to 650 mm normally. So end brackets are very important from understanding point of view. So end brackets, they take care of continuity between subsequent girders. It can accommodate one steel sleeper as shown here. This is one steel sleeper so that the unsupported length of the running rail does not increase beyond permissible limit. Okay. So I hope it has made our discussion has made it clear how the end brackets are provided, what are their functions, and why they are so important. Now, let's move on to the expansion holes. So, expansion hole is another a typical arrangement which is generally followed in longer open web girders. In shorter open web girders, they may be avoided, but typically, if it is more than 60 meters, say, so if it is more than 60 meter, then arrangement of expansion holes is provided. So what is this arrangement? So what happens if this is a long open web girder, and what happens that during temperature rise and fall, the stringers they expand and contract. So longitudinally they expand and contract. So what happens? We provide a stringer expansion arrangement in the form of expansion holes on alternate stringer locations. Okay. So what we do, we provide this slotted hole. This is a slotted hole. This is slotted hole. See it again. Yeah. So these are slotted holes. So what is happening here? That this is a cross girder. Okay. This is a cross girder, and a stringer is getting connected. A stringer is coming like this and is getting terminated like this. So at the bottom flange, we are connecting the stringer with a stool kind of arrangement, which I will show you later. Yeah, this is a kind of a stool arrangement over which this stringer sits, but it is not fixed with the stringer web, cross girder web directly. It is just resting, and it is connected with the help of a bolt, which you can see over here. So here is something like this slotted hole, and a bolt is provided, a loose fitted bolt is provided, which can move in and longitudinally, so that our stringer can move longitudinally, so that it can breathe, it can expand or contract depending upon the temperature. So let's see how typically the section looks like. So this is what the stool kind of arrangement I was talking about. So these are two expansion holes here. So this is what a stool actually looks like. This is a stool arrangement. So our stringer bottom flange will come over here. Here the slotted holes are provided like this. Here this bottom flange of bottom flange of the stringer will come, and like this. This is how, yeah, this is how our stringer will come and sit over my cross girder. This is my cross girder. This entire thing is my cross girder. So I hope you must have understood now how this arrangement is planned. So since the stringers are always in pair, so you can see one stool is here, another is here, and this is already sitting. This is, if you see properly, one stringer is already shown connected. This one, yeah. So with the help of these three photographs, you can see this is a stringer and this is cross girder. This is a stool, and here expansion holes are there in this angle here, and girder moves within that expansion hole. So this is the arrangement. This is a stringer, this is cross girder, this is a stringer, this is cross girder, this is a stool. Okay. So I hope with the help of these photographs, you must have understood that how we take care of expansion and contractions typically providing this expansion hole arrangement in our open web girder on every alternate panel. So this was all about detailing of components. So far for open web girders through type, we have finished general arrangement, we have finished detailing of components. Now let's understand how load transfer takes place. So let's move on to the next lecture. Thank you. Hi. So now we are here. We are going to understand the load transfer mechanism taking place inside a typical open web girder through type. So what is the load transfer sequence? So basically, if we see the upper photograph, so rail wheel will run over these running rails, right? So the first point of contact for transferring the load is these running rails. So the load comes from rail wheels to these running rails. Now these running rails are resting upon these sleepers, these steel sleepers. So the load transfer takes place and load comes to these steel sleepers. Now, these steel sleepers are again resting over stringers. So, stringers we cannot see in the above photograph. So, please come down to this, the photograph below. So, here, if you look carefully, these are the stringers. Okay, these are the stringers. So what happens that we fix steel sleepers like this. We provide a series of steel sleepers like this over the stringers. So steel sleepers are directly resting over stringers. So the load transfer takes place and load comes to the stringers. Now you look carefully. These stringers are connected with these cross girders, right? So the load transfer takes place and the loads comes to the cross girders. So cross girders are provided at every panel point, right? At every panel point they are provided. So at every panel point, this load is getting transferred through cross girders, and in a way, every truss node is participating in mitigating the loads. So finally, entire truss takes part into mitigation of the loads. And finally, as you know, that the bottom chord of the open web girder, the bottom chord of open web girder is resting upon the bearings, right? Is resting upon the bearings. So through bottom chord, the load transfer takes place and load comes upon the bearings. Now, these bearings are again, these bearings like this, these bearings, suppose this is the girder, open web girder, right? These bearings are again resting over some pedestal, and this pedestal is part of a pier cap, and this pier cap is a part of pier. Then it is transferring the load to the foundation. If it is a pile foundation, it's like this. So the load transfer takes place, and from bearing, the load gets transferred to substructure, from substructure to foundation. So to sum it up, we can say that wheel contact takes place and the load from train gets transferred to running rails, from running rails to steel sleepers, from steel sleepers to stringers, from stringers to cross girders, from cross girders to truss nodes to bottom chord to bearings, bearings to substructure, and finally to the foundation and then to the soil. So this is how load transfer takes place. So with this, we have just finished the load transfer sequence in case of open web girder. Now it's time to take up the bearings of the girder. So let's move on to the next lecture. Thank you.
So let's start the topic of bearings of open web girders. So since we are introducing the topic of bearings for the very first time, so let's begin with some basics. So there are some primary functions of the bearings and there are some secondary functions of the bearings. Primary functions include number one, transferring the vertical and horizontal loads. Number two, accommodating movements and accommodating rotations. Okay. And there are some secondary functions like seismic isolation and vertical uplift restraint. If we look at the classification of the bearings, the bearings can be broadly classified into three types: older metal bearings, elastomeric bearings, HLMR bearings. HLMR means high load multi-rotational bearings. So within older metal bearings, we have very popular rocker and roller type bearings, rocker and roller type bearings. Elastomeric bearings, we have plain and reinforced bearings. Reinforced bearings are the ones where inside the rubber pad we have provided steel shims like this. Then we have HLMR bearings. Within HLMR bearings, we have pot PTFE bearings, we have disc bearings, and we have spherical bearings. So let's start with what types of bearings are suitable for open web girders typically. So these three types of bearings are suitable for open web girders: roller and rocker type, pot PTFE, and spherical. So let's see each type of bearing one by one. So first of all, roller and rocker bearing. These are metal-based bearings. Then rocker bearings use spherical steel element. So in the photographs on the right hand side, basically this is fixed end where only a rotation of the girder is to be taken care of. And this is say free end where not only rotation but also the movement, longitudinal movement is also to be taken care of. So this movement is taken care of with the help of these rollers. If I draw it, it is lying inside something like this. There is second one also. It is like this. Yeah. So point number two says that rocker bearings use spherical steel element. So this is the spherical steel element over which convex surface is coinciding with concave surface, and they are providing a kind of arrangement where you know the rotation of the girder can take place. So if we talk about this free end, here on the top plate girder will somewhat come like this. Okay, girder will come like this. Yes. So the rotation of the girder will be taken care of by this spherical steel unit. And roller bearings use cylindrical steel rollers. Where are these cylindrical? Here is one cylindrical steel roller. Okay. Yes. This time. So in combination, they provide movement and rotation. So rollers provide movement, and this rocking arrangement provides rotation. So this movement is provided by rollers, and this rotation is provided by rocker. So where are these? In what conditions? In what cases of open web girders these are suitable? These are suitable for those open web girders where where there are large movements and high rotations. So mostly open web girders are subjected to large movements and high rotations. So these type of roller and rocker type bearings are mostly suitable in most cases of open web girders. And so far, these roller and rocker type arrangement for bearings has served very well in railway transportation system. So these are the by far most popular arrangement for open web girders. The second option was pot PTFE bearing. So let's first understand the various components of a pot PTFE bearing. At the bottommost portion, there is a pot. Inside this pot, this elastomer is put, and over this piston is put. So what happens when load transfer takes place? This elastomer is pressed, compressed, and expanded. So it takes care of the rotation. It takes care of the rotation by differential settlement. Okay. And above this piston, we have PTFE, which serves as a sliding material. So it takes care of sliding movements. And over this PTFE, it is covered by a slide plate. So this is overall arrangement of a pot PTFE type bearing. So let's see point number one, confined elastomeric plate housed in a steel pot and piston chamber. So this is elastomeric plate. It is housed in the piston pot arrangement. Takes care of rotation by differential settlement. And PTFE, which means polytetrafluoroethylene. This takes care of sliding requirements. So this takes care of rotational requirements by differential settlement, and this takes care of sliding movements, uh, the PTFE. So this is how this bearing functions. So in what cases of open web girders these bearings are suitable? So these bearings are suitable where vertical loads are within a range of 2000 kilonewton to 20,000 kilonewton. The girders are subjected to medium to high rotations, that is less than zero point zero 0.04 radians. And as far as spot PTFE, the limit of longitudinal movement is concerned, there is no limit for movement capacity. So these are the specific cases where pot PTFE type open web girders can be adopted. Next is spherical bearings. So in spherical bearings, as far as material is concerned, there is no compression element like elastomer in the pot PTFE bearing. So for rotation, there is no need of any compression element. So basically, it is taken care of. The disc is taking care of rotation. So this is the sliding disc, and this is its rotational interface. It is housed into this cup type of arrangement. So if we see its cross section of sliding disc, so it's something like this. So it's a part of a sphere. It is why it is called a spherical bearing. And this rests upon a interface which just accommodates this surface and allows it to, just do movements like this so that rotational requirements can be taken care of. So there is no material which is getting compressed. So it is a material to material contact, and there is no compression material involved in the whole process. On the top of it, we have sliding material over here, and it is capped by a sliding plate. So this arrangement takes care of this sliding movement. So there is no compression element for rotation. Disc takes care of rotation, and sliding material is provided for sliding requirements. So let's see what are the cases where these spherical bearings are most suitable. These are suitable for medium to very high vertical loads, that is 4,000 kilonewton to 80,000 kilonewton. These are suitable for medium to very high rotations, that is less than zero point 0.10 radians. And if the loading is high and spans are large, then typically spherical bearings are most suitable and economical also. So as a thumb rule, we can say if the span length is more than 60 meter, then spherical bearings can be most conveniently provided, although it depends upon the loading for which girders are being designed. So this was something about spherical bearings. So to conclude this, choice of bearing depends upon specific use case. As we have seen that spherical bearings have applicability in certain load and rotational cases, what PTFE has applicability at different load and rotation use cases. So therefore, it depends upon specific use case, and no bearing can be said superior or inferior to the other. It all depends upon the specific use case. So with this, we have concluded open web girder. So this topic is also complete. So now we have finished open web girders with all the four components covered, and now we can move on to the plate girders. So let's move on to the plate girders. Thank you very much. Yes. So far we have finished open web girders. Now let's move on to the plate girders. So within the plate girders, we will first cover the general arrangement. So this is what a plate girder looks like. This is a solid web girder basically, and track assembly is directly laid over the plate girders. So if we see its cross section, it is something like this. There are two plate girders interconnected with the help of bracings in the middle portion and diaphragm in the end portion. Steel bridge sleepers are provided directly above these girders, over which the rail rests. It's like this. So let's explore plate girders in more detail. So this is what a plate girder looks like. So these are two eye sections. This is one eye section. This is one eye section. And this is another eye section. These two sections are at end connected by a diaphragm, and in the middle they are connected with the help of these cross bracings over a regular interval, and again at the end we have a end diaphragm. The girder itself, if it is longer, then splices are provided as and where required, and along the length of the plate girder on the web, stiffeners are provided. Stiffeners are also provided in the end diaphragm. So this is basically very simple arrangement, easy to understand, nothing more to explain much. So this was an introduction to the plate girder. So let's explore this in more detail. So this is the end diaphragm of plate girder. It is written that two numbers, and this is basically intermediate cross frames, four numbers. So we have just seen that there are two eye sections interconnected at ends by a end diaphragm. Similarly, here also we have two eye sections interconnected in between with the help of intermediate cross frames at regular intervals. And we can also see that this plate girder is having stiffeners. This plate girders are having stiffeners. So this is the basic arrangement of plate girders. So this is the upper figure is the half section of elevation of girder. So as you can see, what
This is the support where the girder is resting over the bearing. This is the plate girder. This is the cross section of the plate girder. Then we have these stiffeners at various places. Then we have splicing arrangement shown when girder is uh, fabricated in parts, so it has to be assembled at site with the help of splices. So splicing is done. So this is the basic arrangement of a plate girder. And if we look at the top plan of the girder, so if we look at the top plan of the girder, it looks something like the figure shown below. So this is the top plan. In the top plan, we can see these, these, these. These are basically top lateral bracings, TLBs. And meanwhile, at regular intervals, we can also see intermediate cross frames. These are intermediate cross frames. This is end diaphragm. This is intermediate cross frame. So we have here end diaphragm. We have these TLBs, top lateral bracings, and then we have intermediate cross frames. So this is the basic arrangement of top of the plate girders. Now let's see the bottom sectional plan of a plate girder. So in the bottom, to start with, we can see it is connected by end diaphragm. Then we have bracings, bottom lateral bracings. We can call it BLBs. And then we have intermediate cross frames. Intermediate cross frames. These are intermediate cross frames. So this is about the bottom plan of the girder. These are the two eye sections. So plate girders are comparatively simpler arrangements. Splicing has also been shown in the figure. This is the splicing. So this was about understanding the general arrangement of plate girders. Now we will continue with the detailing of components in the next lecture. Thank you. Hi. So now we would try to discuss the plate girders, detailing of components. To begin with, the major component of plate girder assembly are the plate girders themselves. They are twin, that is in pair. We have already seen this is one plate girder, this is one plate girder, and at the end it is connected with the help of a end diaphragm, and in the middle portion they are connected with cross frames. Next are the stiffeners. So as we can see, various stiffeners at regular interval have been provided as mentioned in the drawing. They are provided in the plate girder. So this is for stiffening of the long web. Then we have top bracings. So actually, top bracings, top lateral bracings rather. Top lateral bracings we have already seen in the through the drawing. So these are the top lateral bracings. So and the photograph on the right is of composite girder because studs have been provided at the top. In plate girder, these studs, shear studs are not provided. So actually, we could not get any clear photograph of showing TLBs of a plate girder. So just for showing the basic arrangement, we are showing this photograph. So top lateral bracings are given in the same manner in the plate girders also. Okay. Then we have bottom bracings. So as we have seen that this is how bottom bracings are provided between two intermediate cross frames. This is cross frame. This is cross frame. And here again we could not find any suitable photograph for showing a railway plate girder. So that's why we are taking an example of road bridge where we can see the bottom bracings. So actually this is how bottom bracings are provided in the plate girder also. So this is just a representative kind of photo. Now let's move on to cross bracings, or we can say cross frames. So this is how the cross frame is provided. Cross frame is made up of these two members are made up of angles. These two are made up of angles, and then these angles are welded. You can see the welding going like this on the three sides of the angle, like this. So these are welded with the gusset plates. So this is how cross frames are provided. As you can see, the gusset plate over here. This is the gusset plate over here, and the angles over here. These are the angles. Then we have end diaphragm. So this is end diaphragm shown in the drawing, and this is how end diaphragm looks like actually. So in the figure also we have both sides jacking stiffeners provided. So these are basically jacking stiffeners. So the role of jacking stiffeners is that jacks are provided, or rather jacks can be provided just below these, so that during maintenance or other operations you can lift the girders. For example, if you want to inspect the bearing, condition of the bearing, or you want to change the bearing, or you want to do some repair work, you have to lift the girder assembly after detaching the track over it. So if we do not provide these stiffeners, this web can buckle. So to have a strong web, we have provided jacking stiffeners over these end diaphragms. So these are the jacking stiffeners. So this was about detailing of the components. Now let's try to understand the load transfer, how load is transferred from wheels to girders and to the substructures.
So see you in the next lecture. Thank you. So by far we have finished the introduction part. We have finished open web girders and we are now studying plate girders. So now we would understand the load transfer, which is quite simple because plate girders are very simple, very less components. So understanding the load transfer is also simple. So this is our plate girder over which these are the steel sleepers provided. Then we have these running rails, and these are the guard rails. So guard rails are normally non-load bearing rails because only in exceptional cases like derailments, etc., loads come over the guard rails. Otherwise, they are non-load bearing rails. So first of all, the train wheel comes over these running rails, and the load is transferred from running rails to steel sleepers, which is very sorry. The load is transferred from wheels to the running rails. Then it is obvious that from here, from this contact surface, the load is transferred to these sleepers. So from running rails to steel sleepers. Then again, these steel sleepers are resting over the plate girders. So load is transferred from steel sleepers to plate girders. Then these plate girders are resting on some bearings. So the load is transferred to the bearings. And from bearings to this substructure, to this substructure. So then from bearings to substructure, and then from substructure to foundation, and finally to the soil. So this is how the load transfer sequence is there, where the loads from trains are transferred to the soil. So this is quite simple because plate girders are very simple structures. So I hope this simple arrangement could have been understood by the listeners. So thank you. Now we have finished this portion, understanding the load transfer. And now we are at the final stage of this plate girders. Now we will study bearings for the plate girders. Thank you. Yeah, so we are here. We are studying plate girders, and within plate girders, we are going to study bearings of plate girders. So, the most suitable type of bearing for plate girders is elastomeric bearings. So, let's see elastomeric bearings in detail. First of all, let's talk about material. So, material is natural rubber or chloroprene reinforced with steel shims. So, how a elastomeric pad is made? Basically, it is a pad. So, it's a rubber pad, and within rubber, we have steel laminas or steel plates, you can say, uh, inserted at regular intervals. So we have layers of steel plates which are called steel shims. So this is how the rubber of the elastomeric pad is reinforced with steel. So this makes it very powerful, very strong, very weatherproof also. So material is, as we have seen, the natural rubber or chloroprene reinforced with steel shims. So this is something about the material. How it works, it allows rotation by differential compression, and it allows longitudinal movement by shear deformation. So what happens if uh, a girder say is put uh, like this, girder bottom chord is placed like this,
and then it girder deflects. So this portion gets compressed. This gets compressed, and its depth of the pad gets reduced. However, at this end it remains the same. So this is how a kind of slope gets created where depth of girder at one side is lesser than the other side, and this is how girder deflects. So this is how girder deflects. So the rotation is managed by differential compression. Similarly, the longitudinal movement is achieved by a shear deformation. So if this is the pad and girder is trying to, suppose this is the girder resting over this bearing pad, and it moves along this, so along this direction. So the deflected shape of this pad would be something like this. So this is how it it allows longitudinal movement in the girder. So it is very basic arrangement. And uh, what type of plate girders are most suitable where elastomeric bearings can be provided. So they are suitable for elastomeric bearing pads are suitable for small to medium vertical loads like from 200 kilonewton to 2000 kilonewton, and for small movements like less than 100 mm. So this is how this is these are the conditions where we can provide the elastomeric pads uh, for successfully achieving the rotation as well as longitudinal movements. So thank you. So with this, we have finished plate girders. We have covered all these four portions. Now we can move on to composite steel plate girders. Thank you. So by far we have covered introduction part. By far we have covered open web girders and plate girders, and now we are here. We are going to study composite plate girders. So let's start with the general arrangement of composite plate girders. This is how a typical composite plate girder looks like. So the difference between plate girder and a composite plate girder is here the above the girders there is a concrete deck which is provided over the girders. So in the plate girder, track assembly is directly put over the top flange of the plate girders. But here, the top flange of the plate girder is embedded into concrete deck slabs, and basically what you are seeing from here, this is parapet, which stops the track ballast, the track stone ballast from falling on the sides. So, typical cross section of the composite girder looks like this. So here we have I sections. These are the I section plate girders. So like plate girders, there is a pair of steel girders. At end, these are tied with the help of end diaphragm. So here is the end diaphragm, and these are the two steel girders, plate girders. Now above this, we have shear studs welded on the top flange of these girders, which gets cast into the RCC deck slab. These are the parapet walls. These are the parapet walls which stop my ballast. This is how the ballast, stone ballast will be spread over the deck slab, over which we will put the concrete sleeper, over which my rail will come. So this is the arrangement which is followed in the case of composite steel plate girders. In this diagram also, you can see that from the top, you can see we have this sleeper like this. This is center line of the rail, center line of the rail. So here rail will come. Okay. So, and this is typical stone ballast. Then this is deck slab. This is haunch. This is called haunch. This is called haunch. And this is the deck slab. And then this deck slab, below this deck slab, we have I section plate girders, which are at end joined by end diaphragm. So this is how the arrangement is at the end. But if we talk about the intermediate arrangement, we have intermediate cross frames quite similar to the plate girders. The only exception or the only difference here is we do not have we do not have top lateral bracings in the composite girders, whereas in plate girders we had these top lateral bracings also. Here they are not required because this stiffness is achieved with the help of this deck slab, right? So they are permanently casted into my deck slab. They are quite integrated with the help of um, these shear studs. These are called shear studs. So this is how arrangement of composite steel plate girder looks like when we see the intermediate portion of the girders. Here, if you see carefully, 1 in 40 slope has been given to the top of deck slab from here, as you can see, right? So this is because during downpour of rain, the all the water collected inside these parapet walls should be drained away. So in between, we can provide these holes also from where these holes are holes like this in the parapet wall from where water can be dissipated. Now, before going into intricacies of composite steel plate girder, let's understand what composite means here. Here, composite means combined, achieving combined action of RCC and steel for mitigation of the loads and forces which are coming from train to the girders. So, point number one, composite girders aim at taking advantage of properties of different materials. Point number two, steel, which is good in taking loads, is the main beam. Main beam is which is plate girder. But to offset the problems of corrosion in steel and to provide a ballasted track, RCC deck is provided at top. Point number three, concrete, being good in compression, participates as a structural member in compression for the main loads. So this is how the combined effect of RCC and steel is utilized for mitigation of loads transferred from train to the girder. So let's see sketch number one. Here, this is the concrete deck. This is the concrete deck and this is the steel girder. So how to combine these two? Uh, so it should be combined in such a way that both the structural elements behave in unison. So to achieve this, we have to provide embedded shear stud connectors. So shear transfer takes place at steel concrete interface. This is sketch number two. So once casted, these shear studs go inside the concrete, and this concrete portion and this steel portion are now just act as one unit. And if you want to see how these shear studs are arranged or how they look like, let's explore them further. This is how shear studs look like. So they are welded at the top flange of the plate girders. The calculations are done how many series, how many lines of these shear studs are required to transfer the loads correctly, and to achieve the haunch as seen here. As seen here. So here you have seen that there is a haunch kind of arrangement. So this is this is a haunch kind of arrangement. If you look carefully, there is this one. So this is how the shuttering is also done. This is how the shuttering is also done, and this concrete deck slab shuttering is provided in the shape of a haunch. So this girder is ready for pouring the concrete. So in this concrete, these shear studs will be, they will go inside the concrete, and that is how the concrete and steel structural members are united to take the loads in as one unit. So let's see more shear studs in action. So here you can see there are three lines of shear studs provided over the top flange of the plate girders. Here also you can see. So these are the splices. These are the splices, and here also you can see there are three lines which are provided on top flange of the composite plate girder. So some specifications about shear studs. So shear stud symbol is SD1, material or material group or property class. So material group 1 with these limits of carbon, CEV and aluminium. Standards which are followed for shear studs is ISO/TR 15608. Mechanical properties of finished studs. So these are the mechanical properties of shear studs. Rm is the tensile strength of steel, REH is the upper yield of the material, and A5 is the percentage elongation at fracture as per ISO 68921 oblique ISO 13918. So in the field, these shear studs are provided with the help of shear stud gun. This is basically an arc welding process. So with the help of this gun, this shear is put inside, the shear is connected with the top flange. So here do not get confused with this haunch. This is not the haunch prepared and this is not the top flange of the plate girder. This is not the top flange of the plate girder. So basically what is happening here is we have provided this sacrificial shuttering deck slab shuttering material which is in this shape, and this shear stud is here. This is the shear stud actually. This is the shear stud. This is the shear arc stud gun, and this is shear stud. So with the help of arc, this shear gets pierced through this shuttering material, and reaches to the top flange of the girder. So let's see this in action. Now, once installed, it looks like something like this, and below this there is a capping which is of generally of ceramic. It contains the molten metal from flowing outside. So later on, this is broken and removed. Let's see this activity in action. Yeah. So now we have seen how shear studs are fixed to achieve the composite action of RCC and steel. Now here is an interesting video. Um, Actually, this portion, this is a very, detailed microscopic view of stud arc welding. So basically, this is our stud, right? And this is our top flange, you can say, between which the welding is to be done between these two surfaces. So what happens in this portion? Arc action is getting created through shear stud gun. Okay, this gun produces arc. This arc produces heat, and this heat starts melting these two surfaces. This melts, the shear stud melts faster, and if you see carefully, you will see how this shear stud starts melting along with a little bit of melting of this top flange, and how this portion immediately melts away and forms a pool of molten metal, and then our welding is achieved. So let's see this in action. This is very interesting video, and courtesy is to the Cavitar Limited who have released this video. Yes. So you have seen how this shear stud welding is taking place. So you can just observe how fast this process is achieved. Although this the previous video uh, You have seen that much time is taken because the video has been shot in such a way, but it's a very short process as far as time is concerned. As you can see how fast these shear studs can be welded with any surface. So this was about the general arrangement of composite plate girders. Now let's move on to the detailing of components. Thank you. Okay, so now we are going to discuss composite plate girders, detailing of components. So the most important and the most prominent component of composite steel plate girder arrangement is plate girders. They are provided in pair, so there is a twin arrangement of plate girders. So as you can see, this is our plate girder, solid web plate girder. Okay. Then on the top of it, we have these shear studs. So you can see here we have these shear studs. Then to stiffen the web, we have web stiffeners like this. So we have web stiffeners like this. And when the girder is fabricated in parts, so to assemble these parts, we have to do splicing. So these are the splices. These are the splices. So let's move on to the next member component. So next component is the stiffener. So we have already seen as stiffeners are provided in the drawing. So the stiffeners are provided in the actual girder also. We can see over here. Then end diaphragm. So at the end we have this end diaphragm which connects these two girders. So we can see over here, this is basically our end diaphragm. Our end diaphragm has got these jacking stiffeners, these jacking stiffeners. So here you can see these jacking stiffeners below which in case of inspection or maintenance you can place jacks to lift the girder, to lift the girder. Then let's move on to the next component, which is intermediate cross frames. So at the end we have end diaphragms, and now in the intermediate positions we have cross frames as we have discussed earlier. Here is a close look of the cross frame, and here if you look carefully at the top you can see this is the top flange of girder, and in between there is this portion which is of concrete. So this is all concrete. So as the both the both the plate girders are already connected with the help of this deck slab. So that's why we do not need top lateral bracing members at the top. So next we have bottom bracings. As you have seen, these bottom bracings are being provided like this. So in the photograph also you can see these are the bottom bracings of composite plate girder. Now camber is provided in composite plate girders also. So as you can see, the actual shape of our plate girder is something like this. So it has been built with the intention that when load comes, it assumes its normal shape under the load. So camber diagram is always provided by the designer, and girder is fabricated. The girder is fabricated with the dimensions as prescribed in the camber diagram. So let's talk about the GI plate, which is provided at abutment as well as when peer-to-peer, sorry, when girders are provided in series. So this is the GI plate provided between the abutment and the composite steel plate girder, and this is how the arrangement is provided between two. This is one composite plate girder, this is another composite plate girder. So in between we have to provide these, you know, GI plates with this arrangement of, you know, GI plate, angle, and this bolt, etc. So what is the purpose of providing these? The purpose of providing these is basically uh, this stone ballast. This is ballast cushion. This entire thing is ballast cushion. So it should not drop down, or it should not come in between here. So to prevent this falling of ballast, we have to provide a GI plate like this. We have to provide a GI plate like this. So when girder to girder transition is taking place, so we have to provide a GI plate like this. So this prevents falling of stone ballast below. Okay. So this was about detailing of various components. There are very less components in composite steel plate girders. So let's now move on to understand the topic of load transfer in composite plate girders. Thank you. So now we will start understanding the load transfer mechanism of composite plate girder. So this is a typical arrangement of a composite steel plate girder, which I have already explained in the previous lectures. So as you can see here, this is the center line of rail. This is the center line of rail. So this is basically our PSC sleeper over which rail comes. Rail sits over these sleepers like this. So when load comes through rail wheels, the load gets transferred to the running rails. Then the load gets transferred to the concrete sleepers. This is concrete sleeper. This concrete sleeper is basically resting on the ballast cushion. So ballast cushion is nothing but the stone ballast, okay, which provides a cushion kind of thing for transferring and spreading the loads, okay, like this. So now the load has come to the ballast. Now from ballast it will get transferred to this deck slab. So it gets transferred to the concrete deck slab, and extension of this, plate girders in the form of shear stud connectors are within the deck slab itself. So the load easily gets transferred to the plate girders, And now from plate girders, it comes down below to the bearing, from bearing to the pedestal, from pedestal to the pier cap, and from pier cap to the pier and the substructure, and then to the foundation. So it's quite simple. This is how load transfer takes place from rail wheel to the foundation, and then to the soil. I hope it was easy to understand with the help of this figure. So we have completed understanding of load transfer in case of composite steel plate girders. Now for composite steel plate girders, we will study the suitable bearings. Thank you. So now we are going to study composite steel plate girders bearings. So the most suitable bearing for composite plate girders is elastomeric bearing. So this is elastomeric pad. This is elastomeric pad, and we have discussed it in detail in the plate girders portion, but let's discuss again in brief. So here is something about elastic bearings. Let's talk about materials. So natural rubber or chloroprene reinforced with steel shims. So these steel laminas or steel plates which are inserted inside the rubber pad are called steel shims. So it allows rotation by differential compression. It allows longitudinal movement by shear deformation. So we have already discussed these things in plate girder chapter. Then these bearings are basically suitable for small to medium vertical loads from 200 kilonewton to 2000 kilonewton, and for suitable for small movements less than 100 mm as such. So this was about these elastomeric bearings. So now we have finished composite steel plate girder in totality, covering all these four aspects. So now we have finished the introduction portion, and we have finished three types of steel girders. Now we will move on to the rail cum road bridges. Thank you. Hello. So now we have finished the introduction part, and we have also finished these three girders. These three girders we have finished. So now we will start to look into rail cum road bridges. So as we have learned that composite girders, open web girders, and plate girders. These three types of girders are the most adopted designs in the railway transportation system. But apart from these, there are few other types of railway bridges which we must have a look into. So to start with, we will start with the rail cum road bridge. I have taken two examples of rail cum road bridge. One is welded one, another one is bolted one. So let's see first the example number one, which is a welded rail cum road bridge. So a basic structure of a rail cum road bridge is something like this, where sorry, where this road traffic is taken on the upper deck. The road vehicle is taken on the upper deck, and train vehicle is taken on the lower deck. So the reason being, the live load of road traffic is much less in comparison to train loads. So it is always economical from sections and members designing point of view, and that our lever arms are in control as minimum as possible. And overall stability is also good if the heavier loads are placed at the lower levels. So that's why in a typical rail cum road arrangement, it is a common prudence to adopt this arrangement where rail traffic is kept at a lower level and road traffic is kept at upper level. So the configuration and dimension of these lower level girder is defined by schedule of dimension of that particular railway transportation system. Schedule of dimension means where we have defined the maximum moving dimensions of the maximum or biggest vehicle on the railway transportation system. Apart from maximum moving dimension, we have also defined clearances in schedule of dimensions. So overall, we get clear idea what internal clearances, height, etc. has to be kept in while designing the railway bridges. However, for road bridges, road authorities publish special publications where they mention the kind of deck arrangement you have to keep for a certain set of, highway. So in India, there is an organization called IRC, Indian Road Congress, and they publish special publications. They publish special publications. So where they mention what are the deck arrangement for two-lane highway, three-lane highway, and four-lane highways. Apart from this, they also publish a special publication for expressways. So basically, configuration means the width of the carriageway, the footpath arrangement, the curb arrangement, etc. So this is how we get guidance what widths and what deck configuration we have to take for road arrangement. Combining the two together in a rail cum road bridge uh, is quite important because we have to meet the schedule of dimension requirements of railways as well as we have to keep the deck configuration requirements of roads. So this is how we plan a rail cum road bridge. So let's move ahead and see example one, which is an example of welded welded rail cum road bridge. So if we see the top, I mean the road deck of a rail cum road bridge, it looks something like this, very normal. So here, this is the carriageway, this is the footpath, this is you know curb, and there is a small railing and light posts, etc. So this is the top of the deck. And if we go to the lower level of rail cum road bridge, so it looks something like this. So there are two tracks, as you can see, there are two tracks here. Track 1, we may call it, and track 2, we may call it. Then you will easily see that these are the running rails for track 1, and these are the running rails for track 2. Now, these are the guard rails. These are the guard rails for track 1. These are the guard rails for track 2. What are guard rails? We have already explained in the previous chapters. Apart from this, what you can see is these are the members. These are the members of bridge. These are, as you can see, these are fully welded. Fully welded. Nowhere you can see the bolts, etc. because it is a fully welded structure. No bolts. Okay. So we can also see the inspection pathway in between the guardrails. So this is inspection pathway. Also, we can see here cross girders which are visible. So, with the help of the knowledge which we have gained so far, let's try to identify as many members as possible. Well, let's try to, configure the structural arrangement of this rail cum road bridge in the next few slides. So here is another view. So you can see what else is visible over here. So there are basically two trusses. This is truss 1, this is truss 2, These are combined together with the help of these cross girders. These are the cross girders. Okay. So these are the cross girders. What else is visible? Stringers are not visible. So, but we can see these bottom lateral bracings. These bottom lateral bracings. These are the bottom lateral bracings. Then this is the cross girder. Okay, and these are steel bridge sleepers. What else is visible? I think the sway girders are also visible over here. Sway girders are also visible over here, and these are the components of a truss. So these are basically diagonals. There is no vertical over here. Vertical is not provided by design. So next, move on to the next slide. What else is visible over here? Okay, here we can clearly see the arrangement of stringers and how bridge sleepers, steel bridge sleepers have been fitted over it. So these are stringers. Okay, these are stringers. So stringer is here looks like that it is basically an built up I section with the stiffeners provided at few locations. So over these stringers, these I section steel bridge sleepers have been provided. So basically it is I section, but if we this is I section, okay. But if we keep it like this, then it becomes an H. So when the bridge sleeper section is not built up, it's single rolled section and it is having an I section, then we call it H beam sleepers. So these are basically H beam sleepers. Okay, these are steel bridge sleepers, but categorically they can be called H beam sleepers because they are single rolled sections. There is no built up section. So you can also see how they have been put over the stringers, and you can also see, if you see carefully, you can find this hook bolt. Okay, you can find this hook bolt that is used to secure this H-beam sleeper with the top flange of the stringer. And just for your information, please see carefully that there is a small gap. There is a small gap which you can see it is between H-beam sleeper and the top flange of the stringer. There is a small gap. There is always a small gap. Why there is this small gap? What is that thing which is creating this gap? So, just for the information's sake, I must tell you that these steel sleepers, H-beam sleepers or whatever, these steel bridge sleepers are not kept directly over the stringer. There is a small rubber pad, as you can see. There is a small rubber pad which is kept in between steel sleeper and the top flange of the stringer. Why so? Because we want to avoid metal to metal contact, because when train will run over these sleepers, so due to the impact load of the trains, the sleepers will finally damage the top flange of the stringer and vice versa. So to have a cushioning effect, we put a small rubber pads in between, steel sleeper and top flange of the stringer. So if you look carefully, you can also see the cross girders. These are the cross girders. Apart from this, what else is visible? Yes. Please look carefully. These are two holes. These are two holes for providing these hook bolts. Here only one hook bolt has been provided, but since we have two holes, so there is provision of two hook bolts in each, bridge sleeper, H-beam type bridge sleeper. Then you can see there is a small plate over which two projections are there, one and two. What is this? So this is for putting the rail. So the rail is put inside this, like this. The foot of the rail, the section of the rail, if I want to draw, it is something like this. It is something like this. So this foot sits in this portion. So like this, the rail is continuously, put like this, and this is secured, the rail foot is secured with these sleepers with the help of ERC, elastic rail clips. These elastic rail clips go into these holes, these projected holes. These are called inserts. So first we put rail and then we put ERC into these, these inserts so that the rail is secured tightly with the, steel bridge sleepers. Again, we want to avoid metal to metal contact. That's why there is a small rubber pad in between rail, foot, and a steel sleeper. Okay. Now, let's explore a steel bridge sleeper in more detail. If you look carefully, you can also see that here, here, there is a small plate. There is a small plate kept over here. So what is this for? So this is for fixing an accessory over the bridge sleepers, which holds the guardrail. So as you have seen that guardrail is also provided on the bridges. So this is for fixing guardrails. Okay. So let's see some more of the pictures. And yes, one more thing I have found here. This is bottom lateral bracing, which is visible over here. Okay. Next. This is another view. So here you can see that this is cross girder. This is basically a stringer. Okay, so this is a stringer. And these are all, steel sleepers. And you see that this rail is secured with the steel sleeper with the help of these small ERCs, elastic rail clips, which tightly secures it into the, you know, steel bridge sleepers. What else is there? Mm, yeah. So what is this thing? What is this thing? Yes. So as you can imagine that once somebody is on this inspection path and he is inspecting the rails, bridge sleepers, or members, etc. Suddenly, train comes, so he has nowhere to go. So these kind of connecting platforms are provided at regular intervals so that in case the train is approaching, one can come to this platform, and here on the side There is extended platform provided. There is extended platform provided on this side and this side also where a person can stand. So this is for that. So that was it for this, welded type rail come road bridge. So, as you have seen that since we have studied the open web girders in detail with all the components, now even though this rail cum road bridge was new, but you have been able to analyze it, you have been able to identify the key structural components of the bridge, and now you can, just see the bridge and you can imagine what is its anatomy, what are the detailing, what are the components involved, how the structural arrangement of the bridge is. So this is the beauty of understanding the structural mechanism or load transfer mechanism of the bridge. So it helps you to analyze any given bridge, even though you have not studied it, but you are able to imagine how things are working in this particular bridge. Nothing is new to you because you have understood the basics. So, with this, I would like to end this here. In the next lecture, we will see another example of rail cum road bridge, which is, a kind of bolted structure. Thank you. Hi, welcome again. So far we have seen one example of rail cum road bridge, which was a fully welded structure. That was example one. Now we have example two. It is a bolted structure. So bolted structure means these members, individual members, these diagonals, these verticals, these bottom chord members. Individually, they have been fabricated as welded structure, but at the site they have been assembled with the help of bolts. As you can see, here are a series of bolts. Here are a series of bolts visible. Series of bolts visible. Bolts. So these have been assembled with the help of bolts. In the previous example, at site also welding has been done for site connections. Now let's go into some basics of structural arrangement of this particular bridge. So as you know now, with the knowledge of our open web girder lecture, that basically this is bottom chord, these are the diagonals, this is vertical, and here road traffic has been placed, road deck has been placed at top. As you can see on that road deck, these construction equipments are working. So the above portion, in the top portion, we have road deck. At the lower level, we have railway tracks. And these are the piers. This is the pier cap, and this is the pedestal and the bearing, and this is how the general arrangement of this bridge looks like. So let's enter into this bridge. So there are two tracks. This bridge is meant for two tracks. Track number one and track number two will come over here. So it is quite easy to understand now, as the sleepers and track has not been laid over track number two. So we can see internally how the things are arranged, how components have been arranged. So component arrangement is almost similar to any open web girders. So we have these stringers, as you know, these are all stringers. Stringers are always in pairs. So these are stringers, and these are the cross girders. These are the cross girders. So cross girders are given at every panel point. Every panel point we have a cross girder. In between two cross girders, we have one pair of stringers. These stringers are also connected together with the help of, you may call them cross frame or bracings. So as it is visible from here, we can say that this cross girder is having a built-up I section. This is a built-up I section. This yeah, this is this the stringer is also a built-up I section, and these stringers are connected with each other with the help of one channel section in between, and other two angle sections are there to connect these two stringers. Also, we are able to see that there are stiffeners provided over here, over here. So there are stiffeners in the cross girder. Also, some stiffeners are visible in the stringer portion also. And what else is visible over here? So this is the gusset plate at the panel point. This is our vertical. This is our diagonal. And what are these? What are these? So my guess is it is it looks like that, this there is a gap. You can see there is a gap between the two girders. That means one girder is getting terminated over here, and the second girder is getting terminated over here. So these extension pieces are something like end brackets, which we have studied in, you know, open web girders. Now at the end, so we can say that this is the end cross girder, right? This is the end cross girder. So and at these two ends there would be bearings sitting over the pedestals. So for fixing the bearings, and as we have already discussed, for fixing the bearings you have to first lift the girder, or for some maintenance purpose, inspection purpose, you have to lift the girders. So it looks like that these stiffeners, these are jacking stiffeners, provided for putting a jack over here so that the web does not buckle. So this looks like the jacking arrangement. Similar arrangement was with there near the second track. Okay. So there are two jacks. We have the facility of providing two jacks for lifting these, girders. So this was it. What else is visible? As you can see that these are all connections have been made with the help of these bolts. With the help of these bolts. So normally these days, what kind of bolts are used? We use HSFG bolts. What are HSFG bolts? High strength friction grip bolts. So we use high strength friction grip bolts. So unlike normal bolts, they function differently because once they are put, they do not allow the different plies of steel to have, differential movement. They just grip them so that there is no slip between the members. So what does it mean? It creates so much, friction by virtue of, tightening them together, that there is no slip condition, almost no slip condition. So this HSFG bolt bears the shear, etc., with the help of this friction, or rather, but in ordinary bolts, it is the load is mitigated with the help of the shear strength of the shank of the bolt. Unlike this, in friction grip bolts, it is compensated. The shear force is compensated with the help of friction. So this is the basic difference between normal bolts and HSFG bolts.
So nowadays, most of the railway transportation system, and not only railway transportation system, even road authorities, whenever they provide bolts at site, they go for HSFG bolts. These are very common these days. So yeah, now we can see the floor system. So as you can see, this is my bottom chord visible. This is my cross girder. These are the stringers of first track. These are the stringers of second track. Now, apart from this, what else is visible is we have bottom lateral bracings. So, bottom lateral bracings are K type over here, as you can see. This is K type, right? So, bottom lateral bracings are of K type. Uh, Again, I will draw it. This is 1K. Okay, this is another K, right? This is another K. So like this, we have K-type bracings. So K-type bracings have been provided. What else is visible? We can see the bolts. We can see these gusset plates are there. Then what else is visible is what is the section of this bottom lateral bracing. It looks like that section of this cross bracing is the star type. So one angle is like this, another angle is like this, and in between at few intervals we have provided plates. So if I see carefully, see this is one angle, this is another angle, and in between you see this plate, this plate, this plate, and this plate, right? You can see these are the plates which are connecting and making it as a built up section. And how and you can also, if you see carefully, this bottom lateral bracing is connected with the stringer also. This piece is coming from here to here, and this is a bolted with the bottom lateral bracing as well as with the bottom flange of the stringer. Now you see carefully, here it is connected with the bolts, here also it is connected with the bolts. Here it is connected with the second stringer, and here it is connected with the bottom lateral bracing. So this is how these bottom lateral bracings are connected with the stringers. This looks like a solid single rolled section of angle, and these are finally connected with the bottom chord with the help of this gusset. Another extension of BLB emanates from here, right? So this is the structural arrangement of this bottom lateral bracings. Yes, another view. So we have seen the flooring system. So now let's try to identify some more components. So if you see at the top, so this is the top of railway tier. So it is a kind of, it is a kind of sway girder over which the deck slab of road bridge has been provided, connecting the top flange. Top flange of this sway girder must be provided with shear studs, which gets casted into the concrete of road deck. Apart from this, what else is visible? We can see some top lateral bracings over here. Okay, let's see the next photograph. Yes. So here you can see the top arrangement. So this is sway girder kind of arrangement. This is
top lateral bracing, and uh, sway bracings have not been provided because it is again with by virtue of having a deck slab, it's already a rigid, a much stable structure, and to accommodate the road width, the road deck, this extension has been provided in the form of cantilever. So it may be used for platform, for footpath, or something like that. It depends upon the what configuration we have adopted for road bridges. And as you can see over here, there are some extended platform kind of thing. This one. This is inspection pathway provided alongside the girder where a person can move to inspect the bridge or bearings or members or track. So this is in the construction stage. So a pathway sheet will be provided on the floor over which the person can walk, and this is the kind of platform which has been attached with the girder, and it is supported with the help of these angles also. What else is visible? Yeah. So now we can clearly see that what is the top arrangement of this rail cum road bridge. So these are the kind of sway girders, and these are the kind of top lateral bracings, TLBs, and the two sway girders are also connected with I section to provide it have a better stability. And anyway, all of this is has been connected with this deck slab concrete. So as we have seen in the composite steel plate girder, all these components like this way girder, if you want to call it, and this one, and these, all these would have been provided with shear studs at top flange. Shear studs at top flange. So these have been provided with shear studs at the top flange, and at the time of casting of concrete, those must have gone inside the concrete. And you can also see, if you see carefully, that a haunch kind of arrangement is there. A haunch kind of arrangement is there around this, right? Yes. So, so you can easily find that with the help of our knowledge of fundamentals of the components of open web girders, we are able to easily identify what are the structural elements of this particular bridge, although we have not, studied it previously. But now we can identify what are the key structural components in any new bridge, although we have not studied it, and we can conceptualize what is the load transfer mechanism with in mind with which the bridge has been designed. So this is the beauty of understanding the fundamentals. You can now analyze any kind of railway bridge or rail cum road bridge because you have understood the basics around these bridges. So it's a great power to you, and I hope it will be very useful for you, whether you are in design or you are a practicing bridge engineer involved into the construction, maintenance, or inspection of these bridges. Thank you. Hi. So in this lecture, we will see ballasted deck open web girder. So let's see. So what this is ballasted deck open web girder, and this is normal through type open web girder with steel sleepers. So, what is the difference? So, basically, the difference lies in the way the track is being laid over the girder, and also in the way the load is getting transferred from bridge to substructure. from rail to bridge and bridge to substructure. So what is the difference as far as track is concerned? So the first difference is that in this in the first case here, the track is being laid over steel channel sleepers. Especially these are especially fabricated for providing over bridges only. But in this case, however, we have this concrete deck. So these are parapet walls. These are parapet walls, and this is concrete deck. So this concrete deck is used for spreading the stone ballast, and over this stone ballast, we can continue our ordinary track just like we are continuing it with on of our earthen embankments. So normal track like a stone ballast, concrete sleepers and rails that can be continued over our bridge also. We do not need to have a special kind of steel sleepers for laying that track over the ballasted deck open web girders. So this is the first difference. The second difference lies in load transfer mechanism. So here the load mitigation arrangement is based upon the behavior of steel as a truss. But here composite action of the composite action is being utilized. Composite action of what? Composite action of RCC and steel is being utilized for mitigating the loads and forces which are getting transferred from train to the bridge. So this was the difference. So this is normal open web girder through type. This is also through type, but this is open web girder with ballasted deck. Concrete deck is there over which ballast is provided. So that's why it is called ballasted deck. So let's see next. Yeah, so this is elevation of the same girder from one side. So on this side, an inspection platform, this is inspection platform is attached with the bottom chord. So this inspection platform can be utilized by inspecting officials to move across the bridge, without getting affected by movement of trains. They can safely walk from one end of the bridge to the other end, duly inspecting the bridge components and track components. So let's revise our basic structural elements. So this is end raker. This is our top chord. This is also top chord. Then we have these verticals. We have these diagonals. Then here we can see clearly this is sway girder, and these are top lateral bracings. And here we have portal girder, and these are the portal bracings. So this is an overall arrangement, and one thing more is here. We can see here this is our sway bracing. So overall arrangement is more or less similar to the normal steel through type girder, through type open web girder. So let's see it from uh, other side from one end. So this is basically end raker. It is a lattice type, lacing type uh, component. Then what else is visible over here? This is vertical, this is diagonal, and again this is top lateral bracing. We can see this portal girder over here, and these are portal bracings provided over here. As usual, this is our concrete deck. This is parapet wall, and stone ballast can be easily spread on the deck, and ordinary concrete sleepers track can be continued over the bridge also without any difficulty. So let's move on to the next. So this is another view of this girder. On one side, that the inspection platform has been attached with the bottom cord. So bottom cord was not clearly visible. From this side, this bottom cord is clearly visible, right? We can also see this pier caps over which the girder is resting, and other members we have already explained. So let's move on to the next. Yeah. So this picture clearly shows our inspection platform. So this is our inspection platform. Our inspecting officials can move on this inspection platform safely without having any kind of botheration of train movement in mind. So they can peacefully do their work. They can inspect the connections. They can inspect the health of the members. They can inspect the health of the uh, you know uh, track also. So this is for that purpose, and this is attached with the bottom cord. This inspection platform is attached with the bottom cord. This is obviously the parapet of the deck, RCC deck, ballast deck. Yeah, this is important. This is basically the flooring system of the ballasted deck open web girder. So what is visible over here? So this is my bottom chord. This is also my bottom chord. This is inspection platform, clearly visible from bottom. Then what else do we have? This is our cross girder. This is basically stringer. This is also a stringer. These are stringers. Then what else is visible? So yes, you can see some wooden pieces over here and some red plywood visible over here. So probably this photograph has been taken just after the casting of concrete deck. So this is basically shuttering material which has not been removed yet. It will be removed and then the concrete itself would be clearly visible. But let's ignore for the time being. So what else is visible? The two stringers are connected with the help of ISMC or channel sections, like this, like this, like this. And again, these are connected with the help of angles as bracings. So yes, so this is a kind of connection arrangement between the two stringers. What else is visible? Yes, the bottom lateral bracing is also visible. Bottom lateral bracing is having a star section. Star is something like this, one angle, another angle, and in between, time to time we provide plate so that this is a small plate provided over here as you can see. So this makes the built-up section of BLB, bottom lateral bracing, and what the section we make is called a star section. This is called a star section. One angle, another angle connected with the help of plate. Again, if you see carefully, this star section bottom lateral bracing is uh, connected with the stringers also. As you can see over here, there is a connection planned with the stringer here, here. If you look closer, here you can see this. So this is a plate like this. So the top is connected with the stringer, and this portion is connected with the bottom lateral bracing. So this is how this connection is planned. And again, this bottom lateral bracing is connected with this gusset plate. This gusset plate is basically connecting bottom cords, bottom lateral bracings, and cross girder.
So you have seen how, with the basic knowledge of open web girdle, we have analyzed this new kind of ballasted or blasted deck open web girder. So now we are able to analyze new kinds of bridges with the help of the fundamentals that we have learned in the previous lectures. So I hope this was useful, and this is how we can see through the key structural components of any bridge, and we can think, we can visualize, and we can apply our mind while designing or inspecting or constructing or maintaining these bridge assets. So with this lecture, we have now completed this ballasted deck open web girder, and now we will move on to selection of a suitable girder in specific use cases. Thank you. Hi. So far we have covered introduction part and all possible types of railway steel girders. Now let's come to the topic of selection of suitable steel girder for a specific use case, where you are interested in finding out which kind of railway steel girder is suitable for my specific case. So what are those factors which govern this choice? So we will start with the very obvious, parameter, that is number one, requirement of traffic. What is the requirement of the traffic? Whether it is only rail or rail come road. So if it is only rail, we can go for any railway steel type girder, and if it has to serve both railway transportation as well as road transportation, then we have to go again for rail come road bridge. Then comes the speed. So speed is very important consideration for selection of type of steel girder. So a study has been conducted, and it has been found that the girders which are having concrete deck, like we have seen two cases where we have composite composite girders. Then we have ballasted deck open web girders where concrete decks are there. So in the study, it has been found that beyond 200 kmph speed, the girders provided with deck slab, like we have provided in composite and ballasted deck open web girders, are suitable for higher speeds, and the girders which are not provided with concrete decks are not suitable for these higher speeds. So when we say high speed, so if we want to design our girder for higher speeds, then it has to be checked for certain parameters which we do not check in design otherwise for lesser speeds, say 160 or 170 kmph. So what happens that for the lower speeds like 160 kmph or 170 kmph, our static analysis of stress and strain method is sufficient to analyze and design these bridges. But when we want to go for bridges suitable for higher speeds like 200 kmph and beyond, so we have to perform dynamic analysis for these bridges, because there are certain parameters which are now required to be checked for these bridges, which otherwise do not come into picture in static analysis which is performed for lower speed bridges. So what happens that the design of bridges for higher speed trains must satisfy the limits for these parameters. What are those parameters? So I will name a few. Like we have to see what is the maximum vertical displacement, what is the maximum vertical deck acceleration, what is the maximum vertical and horizontal angular rotations, what is the maximum vertical alignment irregularity. So these factors come into picture, and we have to follow the stringent limits uh, for designing these bridges. So, as per the study conducted, as I have already explained, the railway girders with deck slabs like composite steel plate girders and ballasted deck open web girders are mostly suitable for higher speeds. So definitely our choice is governed by the speed for which we want to design our bridges. And when one thing is for your information that when we say speed, so mostly speed limit is decided by passenger trains and not by the goods trains. So because passenger trains operate at much higher speed than the goods train. Now, the third parameter which decides the choice of a girder per type is span. So if we talk about a span, so for smaller spans, say up to 30-meter, plate girder and composite type of girders are suitable. And for larger spans, more than 30-meter, we should go for open web girders. So although I have already explained, but I will explain it again here. So here you are seeing plate girders. So this is peer to peer one span, say L1, and this is peer to peer second span, say L2. So this L1 is greater than L2, right? So higher the span, the greater is the depth of the girder, right? And lower the span, the lower is the depth of the girder. So what happens that as we keep on increasing the span, the depth of this plate girder goes on increasing. So if we are crossing a water body or some canal or some river or something, we have some navigational requirements like freeboard. Freeboard. What is freeboard? Freeboard is the vertical height difference between bottom of the girder to the highest water level. So this minimum freeboard requirement is there, which we should satisfy in our planning. So this is fixed. We cannot go below this level, say, because if we go, we cannot meet the freeboard requirements as mandated by the water body authorities. Now, what is the option? So if we increase our span from here, so suppose this is our limit beyond which down we cannot go. So if we increase our span, now the rail level which is currently here, so it will come somewhere here. If we again increase, then it will come over here, then it will come over here. So like that, this span, this depth of plate girder will keep on increasing. So it creates two problems. Number one, the structure itself becomes unstable as we move beyond a certain limit of girder depth. The stability of this web, the structural adequacy of this web is questionable as we go beyond a certain limit, and we have to provide special arrangements for holding these plate girders together and perform safely under the train loads. The second problem is there is an approach and the track which is coming from approach to the bridge has got a certain level. So we cannot go, beyond a reasonable limit at the bridge location because then we have to ramp it down to match it with the normal ground level somewhere in the approach. So this length of the ramp will go on, the length of this ramp will go on increasing if we increase the depth of the girder. So because of these limitations, it has been observed that up to 30-meter plate girders and composite girders are suitable and beyond 30-meter open web girders are the natural choice. Then comes the navigational requirements, as I have already explained. What are these navigational requirements? Number one is freeboard.
Freeboard is the height from highest water level to girder bottom. I have already explained how this freeboard has a bearing upon the choice of girder type which we want to use for our specific use case. The second navigational requirement is basically waterway. So why these requirements are there because of freeboard and waterway? Waterway is basically peer-to-peer clearance. Peer-to-peer clear waterway is the definition of the waterway. So why these requirements are there? Because if we put piers in the middle of the river body, we want to send ships or boats, and we have some navigational requirements of height and width so that these ships and boats can easily, safely pass through the bridge, under the bridge. So we cannot go beyond those limits. We cannot restrict them. Otherwise, the waterway authorities will not pass the planning scheme of our bridge. So that's why we have requirements of freeboard and waterway. So how freeboard affects our choice, we have already seen how waterway affects our choice because waterway, the clear waterway decides the clear waterway decides this one. The clear waterway decides the span of the bridge. So again, we have come back to this thing, span, and is how span decides the choice of girder we have seen. So, in nutshell, we can say that requirement of traffic, speed, span, and navigational requirements, these four things decide our choice of girder type for a specific use case. Obviously, there can be other parameters also which needs to be taken care of, but these are the four basic parameters which we need to analyze while deciding what girder type we are going to use in our specific use case. Thank you. Hi. So we are at the last session of this course, that is track structure over bridges. So the bridges which are provided with concrete decks like composite plate girder or ballasted deck open web girders. So there is no problem in continuing the existing track structure over the bridge also. Here is the bridge. So we can continue with the same kind of stone ballast, concrete sleepers, railway track assembly over the bridge portion also. So there is no problem in composite plate girders and ballasted deck open web girders where we have provided concrete decks with parapets. Now we need special arrangements if the concrete deck is not there. So this is what a special arrangement looks like. So these are all the special steel sleepers. So steel sleepers, if we talk about steel sleepers, basically they are of two types. Number one is channel sleepers and number two is H-beam sleepers. Channel sleeper is a built-up section made out of two channel sections, ISMC sections or C sections, like this. And H-beam sleeper is made up of uh, I section, I section, uh, this is made up of I section. So So these are the two types of steel sleepers. We will discuss them one by one. So let's start with the channel sleepers. So what you are seeing here is basically channel sleeper, which is made up of two ISMC sections. So this is how the running rail is fixed with the channel sleeper, and this is how the guard rail is fixed with the channel sleepers. And inspection pathway, this is inspection pathway. It is simply bolted at 2 points on each sleeper like this. Okay. So this channel sleeper is basically resting upon the stringer top flange, and the stringers are in turn resting on these cross girders. So this is the basic arrangement. Then I would like to show you with the help of this drawing. So this entire thing is a cross girder basically. Here it is written cross girder. This is the bottom flange. This is the top flange of the cross girder. On this cross girder, two stringers are getting attached. This is one stringer. This is second stringer, right? So on the top flange, this is the top flange of the stringer, this is the top flange of the stringer. Steel bridge sleeper comes and sits like this. Okay, so this is how steel bridge sleeper is sitting on the top flange of the stringer. Then we provide a hook bolt. Sorry, then we provide a hook bolt like this which holds these sleepers tightly, on the stringers. Then fastenings are provided over here in the form of nuts, and this is how we secure these steel bridge sleepers over the stringers. And this is how our running rail comes. And here is the guardrail. Okay, yeah. And here is the inspection platform fitted. So this is running rail, this is also running rail, this is hook bolt, these are two guardrails, and this is inspection platform. Now, just if we remove the sleepers, this photograph is just to make clear what is the arrangement of cross girder and stringer connection, right? So it is clearly visible over here, and the steel sleepers are just placed over them like this, and holding down bolt goes like this. So again, if we look carefully, this is our cross girder, and this is the top flange. This is the top flange of stringer, right? And this is my running rail. This is my guard rail, right? And this is my inspection pathway, and this is the top portion of my hook bolts. Okay, so there is only one hook bolt for each channel sleeper. The cross section of this sleeper is this two channels. So let's have a closer look. This is a channel section. This is another channel section. And with the help of these two, we have built a built-up section which is used as steel channel sleeper, right? Okay. Now, what other members are? So basically, this is my running rail. This is my guardrail, right? This is this is the holding arrangement of these running rails. And if we look carefully, we can see rubber pad placed between the foot of the rail. This is foot of the rail and the steel channel sleeper. And there is a smaller rubber pad which is also provided below the guardrail to avoid metal to metal contact. And what else? Yes, these are the stiffeners. These are the stiffeners provided for below the rail seat because the rail wheel load will directly transfer its load at this location, right? At this location. From here, the load will be transferred through rails to this location of the bridge. So that's why stiffening is necessary at this location. So stiffeners have been provided. So actually in the field, this is how we fix these steel channel sleepers on plate girders or any other girder. So these are the channel sections built combined together to form a steel channel sleeper. So these are all steel channel sleepers. This is the running rail. This is also running rail. In between we have these two guard rails and these are the holding down bolts. These are the holding down bolts which are put to connect securely the steel channel sleepers with the stringers. So this hook bolt goes like this and secures my steel channel sleeper with the top flange tightly. Yeah, so this was about a steel channel sleeper, and let's have a closer look of how this holding down bolt goes through the steel channel sleeper and connects with the top flange of the stringer. This is the top flange of the stringer, and these are the channel sections with help of which the steel channel sleeper has been made. So this is my steel channel sleeper. This is my stringer. This is the top flange of the stringer, and this is how bolts hook bolts hook bolt holds it. This is how hook bolt holds it. Right? Now let's have a more closer look on the rubber pads. So this is my channel sleeper and this is the top flange of my stringer. In between the two, we have to provide rubber pad like this, okay, so that metal to metal contact is avoided because impact loads of the train can damage the stringer flange also and channel slipper also if these rubber pads are not provided. Similarly, this is the foot of running rail which is put just above this top flange of the channel slipper and in between we have to provide this rubber pad so that direct metal to metal contact can be avoided. This is more clearly visible in this picture. So these are my two channel sweepers and this is the top flange of my stringer. In between we have provided these rubber pads. Okay. Also between running rail and channel sleeper, these thicker rubber pads have been provided and this one is the guardrail. See, a small rubber pad of approximately 6 to 7 mm has been provided over here also. So this was all about steel channel sleepers, right? So I said that there is one steel channel sleeper and there is another steel H-beam sleeper. So now we will see H-beam sleeper. So H-beam sleeper is nothing but a rolled section, I section. Okay. So
here we can see this is basically running rail. This is basically a guardrail, and running rail here is attached with the H-beam sleeper with the help of elastic rail clips for which inserts are already provided in the H-beam assembly. Below my below the foot of running rail, we have to provide rubber pad. Rubber pad has also been provided below the foot of the guardrail. Okay, now let's have a closer look over here. This is an I section H-beam sleeper. This is running rail. This is guardrail, and this is called elastic rail clip, which is an standard accessory of fixing the rails with the sleepers. This ERC goes into this thing which is called insert. Thereafter we can see small rubber pad over here below the foot of running rail. There is a small rubber pad here also below the guardrails, and we can easily see this is the hook bolt which is holding this rubber pad, which will come in between H-beam sleeper and top flange of stringer. So right now it is holding this rubber pad, otherwise it will go below this also and it will hold top flange of the sleeper. So let's have a practical application of H-beam sleeper. So, and yes, one thing is to be seen carefully that there is provision of two hook bolts in H-beam sleepers, whereas there was only one hook bolt in, only one hook bolt in each sleeper in case of channel sleepers. So in H-beam sleepers, we have provision of two hook bolts. See, two holes are there, so two hook bolts can be provided like this. Yeah. And so in this particular case, you can easily see this is the cross girder, these are stringers, and H beam sleepers of I section have been provided. These are holding down hook bolts basically. These are inserts over which rails can be fixed with the help of elastic rail clips. So, and yes, you can see these rubber pads also. You can see these rubber pads also. So, with this, we have understood the track structure over bridges. So, now we have completed the introduction part. Then we have seen what are various type of railway steel girders. And now we have completed track structure over bridges. So, congratulations to all of the attendees for successfully completing this course, A Practical Guide to Railway Steel Girders.